Good morning. So first, I'll discuss about the non-recursive binary tree traversal. So we have in-order non-recursive tree traversal included for your lab. So first, I'll try to discuss about that program, and then we will discuss about height balanced binary trees. Okay. So already you have written the program for implementing the binary tree, and then followed by, so we have implemented three types of recursive tree traversals: in-order recursive, pre-order recursive, and post-order recursive. So to continue the same, in this class, we will discuss about the non-recursive tree traversals. See, non-recursive tree traversals in the sense, recursion by default or implicitly uses a stack for the implementation of recursion. So whenever a recursive function call is invoked, so the address of the next statement will be pushed onto the stack, and then recursively the same function will be called with once again with the set of parameters with which it is invoked. So while discussing the stack applications, I discussed about recursive function calls also. Now, in this class, we will see, without using recursion, how we can implement a binary tree traversal. Okay, so specifically, I discussed for in-order non-recursive tree traversal. The algorithm is very simple. So first, I'll try to explain the algorithm using an example. Then I'll explain the function. So here, when you want to remove recursion, so obviously you have to implement stack by yourself. So generally, whenever we want to avoid recursion, so recursion implicitly uses stack. If I want to avoid recursion, what I have to do? So I have to use a stack by myself. I have to create a stack, and I have to use that stack for storing the nodes data temporarily. So the same thing I do it here. So first you take a stack. Now this stack you require, so the stack that you have to consider has to store nodes or addresses of the nodes. So what you can do is, already we have implemented stack ADT, the same stack ADT. So whether you can use the stack implementation using arrays or using linked list, whichever you want, you can use it. So in that ADT, so we used it for storing, I think ADT means, so we have created it with as a generic template. So using class template. So the same class template, that program you copy and paste in this. So I have shared the full program in your WhatsApp group just before this class. You just go through that. So if you don't want to use that, I'll try when I explain the program, I'll try to explain that. So first, let me explain using an example. So non-recursive binary tree traversal. In-order non-recursive binary tree traversal. So take a temporary pointer, make it point to the root node. Okay, make it point to the root node. So what we have to do is push this node. So to whatever node your temporary pointer is pointing to, you push the node onto the stack, and then check whether this node has left child. If it has left child, move this temporary pointer towards its left child. So once again, follow the same procedure. So push this node onto the stack. So B, does it have left child? No. When you reach a node with no left child, so your pushing the nodes operation has to stop. So what is the first step? So the first step in the algorithm is, say, take a temporary pointer and make it point to the root. Okay. So if root node is not null, you push the root node onto the stack and make this temporary pointer point towards its left child. So moving towards its left child, this operation you should continue until you reach a node with no more left child. So B does not have a left child, so we have stopped. So A, we have pushed. So I made this temporary pointer point towards its left child. So once again I pushed it. Then I have checked whether it has left child. It does not have left child. So you have to stop. Then what is the next step? So pop out the node. When you reach a node with no further left chain, so what we have to do? Pop out a node. Okay, pop means so the topmost node gets popped out. Okay, and then you display. I'll write the output. Display the node. So what is the data in this node B? I'll display it. Then check whether it has a right chain. If it has a right chain, then make your temporary pointer point towards its right chain. So here B does not have a right chain. If it does not have a right chain, check whether any node is pending in the stack. Yes. So pop it out. So pop out and display, and then check whether it has any right chain. Now it has a right chain. So make this temporary pointer point to C. So once again, same procedure. Push C onto the stack and then make this temporary pointer point towards its left chain. So R now points to D. Push it. So does D have a left chain? No. We have reached a node which does not have a left chain. There you have to stop your traversal. So now when you reach a node with no more left chain or with no left chain, so check whether any nodes are pending in the stack. If they are pending, so what is the procedure? Pop out and display, and then check whether this D has a right chain. If it has a D, if D has a right chain, once again you have to follow the same procedure. Make the temporary pointer point to its right chain, push it onto the stack. If it has a left chain, then move the temporary pointer towards its left chain. So D does not have a. So now once again pop out. So C gets popped out. So now display the data and then let's check whether it has right chain. If it has right chain, make the temporary pointer. Once again push this E. Does it have a left chain? No. So now E does not have a left chain. So pop out E and display. Now here E does not have a right chain and check the status of the stack. Now stack is also empty. When your stack is empty, you can stop your traversal. Okay. So now what is the output? Now you see B, A, B, C, E. Now just perform in-order traversal. So in-order traversal is so left node right. So first B will come. So for this left chain. So A's left chain is completed. So traverse A. So now right chain. Before this, it has a left chain. So B, C, B, A, B, C. Here also B, A, B, C. So now this in-order traversal. So non-recursive in-order traversal. Okay. So can anybody explain this? Now I have explained algorithm. No, 3 steps. You can explain. You unmute your mic and explain the 3 steps. Just list out the 3 steps. Not explanation is not required. So what is the first step? So take a temporary pointer, make it point to the root node. So that is the first step. So push the root node onto the stack and check whether the root node has left chain. If it has left chain, so make this temporary pointer point towards its left chain and continue the same step. So push this node onto the stack and check whether it has left chain. If it has left chain, so push this node onto the stack and move the temporary pointer towards its left chain. But so this is the first step. Second step is when your temporary pointer is pointing to a node which does not have a left chain, then what we have to do? So you have to check the status of the stack. So if the stack holds some nodes, or in this stack if there are some nodes stored already, pop out the topmost node and then display it. Okay, pop out the topmost node and then display it. Then the third step is, so check whether the popped out node has a right chain. If the popped out node has a right chain, then make the temporary pointer point towards its right chain and you continue with the same steps. Push this node onto the stack. If it has left chain, move the temporary pointer towards its left chain. So you have to continue this process until your stack is empty. Until your stack is empty. So these are the 3 steps that we need to follow. Okay. So this is the algorithm for in-order non-recursive tree traversal. Non-recursive binary tree traversal to be precise. Yes. Did you understand? Do you have any problem? Shall we take another example? Okay. Let us consider a more complicated example. A, B, C, D, E, F, G. Yeah, 16, you please unmute your mic. Can you help me? Yeah, 16, unmute your mic. See, be attentive. Simply logging into the class and if you're not attentive, then there is no purpose. See, ultimately, who is the loser? Huh? Giving absent, all that. See, you're all professional students, not nursery students or say upper primary school students. You have to be attentive. Otherwise, see, simply logging in for the sake of attendance does not give any mileage to you. It's unnecessarily. If you say, sir, we don't want 15 minutes, I'll stop. Yeah, 40, please unmute your mic. Unmute your mic.
Yes, sir.
Yeah, tell me. Okay. So first, we'll make the temporary pointer point to A. Now, what is the second step? What we have to do?
We have to check the left chain, sir.
Yeah, it has left chain. But before checking, we need to do one more operation. What is that
We have
operation?
to point it to a temporary node.
So first, R is pointing to the root node. Push this root node onto the stack. First, you have to push and then make it point towards its left chain. So B, push it onto stack and then you have to make this R point towards its left chain. But B does not have a left chain, so you have to stop. So we have reached the farthest left chain. So B does not have further left chain. When you reach a node with no more left chain, next, what is the next step? So this is the first step. Second step is pop out the node and display. So if you pop out, B gets popped out. And then check whether B has a right chain. If B has a right chain, then continue step 1. B, does it have right chain? No. So what we have to do, check whether any nodes are pending in the stack. Yes. So pop out and display. A, pop out and display. So then check A has right chain. Yes. So make the temporary pointer point towards its right chain. Then continue with the step 1. So push C. Then push D. D does not have a left chain. So we have reached this dead end. So what we have to do? Pop out, display. So D, does it have right chain? No. C, pop out, display. C, does it have right chain? Yes. Make this temporary pointer point towards its right chain. So once again, continue. So E, push it. Make R point towards its left chain. F, push it. So we have reached the farthest left chain. F does not have further left chain. So now what we have to do? Pop out and display and then check whether F has a right chain. No, it does not have right chain. E, pop out and display. Check whether it has right chain. Yes. So make this temporary pointer point to this. So push G on this stack. So now G does not have a left chain. So sorry, pop out G and display it. G, does it have a right chain? So finally, when there are no more nodes or when your stack is empty, you can stop your travels. you can stop your traversal. So this is how you have to perform non-recursive in-order binary tree traversal. So just visualize how I did. If you have any doubt, you ask me. Okay. Now I'll try to explain this function. So I have written only function. Why? Because this program, full program requires stack implementation. So already we have implemented stack ADT. You just copy that program, generic stack program into this, and you can start using the same program here. Okay. So now let us see A, B, C, E, E. Okay. Now see, so what is this small r? Small r is a temporary pointer. So here you have to pass root node as the actual parameter. So small r is the name of the formal parameter. So when you pass root node as the actual parameter, r will become formal parameter. R now points to the same node to which your root is pointing to. Okay. Now you see, we are taking a temporary pointer, CUR, and we are assigning R to CUR. So CUR now points to the same root node. Okay. So S is a stack object. So already you have to create a stack class. For this, I'm creating an object. Okay. So what is, see, when you are creating an object, say if you simply copy the stack linked list program or stack using array program here. So when you are creating a stack object, you have to create this in such a way that it should store what binary tree nodes. So earlier we have used stack for storing integers, for storing characters. But here in this application, I want a stack which can store binary tree nodes. So that's why here you have to tell what is the type. So binary tree node. So like this you have to do. So S is an object which can store binary tree nodes, not an integer, not a character. It should accommodate binary tree nodes. So you know the structure of binary tree node. It consists of 3 fields. So left pointer, right pointer, and then info field. Okay, am I right? So this is how you have to do it. So S is a such type of object. Now you know what is this empty. So empty function. So I don't know whether we have defined a stack with empty or not. So this empty function, whenever it is called on stack or any other data structure, if your data structure is empty, it returns true. If there are some elements stored in that data structure, it returns false. Okay. Now let us see. So initially your stack is empty. Okay, top would be -1. So this is 0, 1, 2, 3. So when top is equal to -1, so this empty will return true. Now you will tell me S dot empty. Is it empty? Yes. So this will return true. True equal to false. What happens to this condition? So true is equal to false. So this condition becomes false. Okay, this is false. Or we are using logical OR. What is the second condition? Current is not equal to null. Yes, current is not equal to null. It is pointing to the root. So because we are using logical OR, so when one of these conditions is true, the whole condition becomes true. Now we will enter into the loop, while loop. So this is the beginning of the while loop, and this is the end of the while loop. Once again, we are checking whether we have entered into the loop with this condition, second condition. Current is not equal to null. Yes. If this condition is true, what is that we are doing? You see. First step is S dot push CUR. What is CUR? A. A node will be pushed. So top now will become 0. Top points to this. So first top will be incremented, top plus plus, and then so stack of top we are inserting this node. What is this node? A. After that, what is the next step? current is equal to current left. So current now points to current left. That is B. So once again, this is the inner while loop. Current is not equal to null. Yes, current is not equal to null. So S dot push. So top now becomes 1. So what is this node B? B will be pushed and your top will be pointing to first. And then current is equal to current left. What is this current left? You tell me. B, does it have left? No. So current is equal to current left means current now will become null because the left chain of B is null. So current left. So current is, so you see, what is current left? Current is pointing to this node. This node left would be null. So we are assigning null to CUR. CUR will become null. Once again, you go back. CUR. What is CUR? Null. Null not equal to null condition becomes false. So we come out of this. So first step is make the temporary pointer point to the root node, push it onto the stack, check whether it has left chain. If it has left chain, move towards its left chain, push it. So continue this process until you reach a node with no further left chain or with no left chain. So B does not have left chain. So this loop continues. Now next step is you have to pop out a node and make the temporary pointer. Sorry, you have to pop out a node and then display that node and then check whether that popped out node has a right chain. That is what we are doing here. CUR is equal to S dot pop. When you perform S dot pop, what happens? B node will be popped out. So your top once again becomes 0, it points to A. So your CUR becomes B. Okay. So now you see S dot pop, B will be popped and we are assigning to CUR. So CUR now points to B. And then I'll write the output here. This output here. S dot info. What is S dot info? B. B will be displayed. After B, we are displaying a blank space. Okay. Or otherwise an arrow, that is better. And then you see CUR is equal to CUR right. CUR, what is CUR right? CUR is pointing to B. B, does it have right chain? No. Once again, CUR will become none. So once again, you will go back. Okay. So where you will go back? So once again, you will go back here. See what happens. Now you tell me S dot empty. What is S dot empty? Is your stack empty? No, stack has node A. So S dot empty will return what it will return? False.
False.
It returns false. False equal to false? Yes. First condition is true, so we'll enter into the loop. Now you see current is not equal to null. What is current value now? Current is null. So current is not equal to null condition becomes false. So we will come here. So this is this loop. We'll come out of this inner loop. S dot pop to C. So when you say S dot pop, so what happens? A gets popped out. So your R now, sorry, your CUR now points to A. Okay. So S dot pop means A node gets popped out, and then we are assigning this to CUR. So CUR now once again points to A. Then you see, okay, what is the next step? CUR info. What is CUR info? CUR is pointing to A. So A info, the node that is stored in that. So the node to which CUR is pointing to, that node's info we are displaying. That is A. Then CUR is equal to CUR right. So CUR has right? Yes. Okay. Then once again you go back. S dot in. So S dot empty. What is S dot empty? What does it return now? Yes, it returns true. Okay. S dot empty is true. So true is equal to false. First condition is false. Now we'll check the status of the second condition. Current is not equal to null. Yes. This condition now will become true. Current is not null. It is pointing to C. Yes. Next, we will come here. Current is not equal to null. S dot push. So C will be pushed. So once again, top will become 0. Okay. So actually, these nodes will be deleted. So better. So C will be pushed as 0th element. So your top will be pointing to this. Okay. Push. CUR is equal to CUR left. CUR is equal to CUR left. So once again, CUR is not equal to null. Yes. Push. So D will be pushed. Top now points to this. Okay. Once again, CUR is not equal to null. Okay. So CUR is equal to CUR left. This statement. So CUR is not equal to null. Yes. The top now becomes 2. So F will be inserted and your top now points to this. So until left child is null, so you will keep on pushing the nodes. So this is the current status of the stack. So after this, so next, after pushing, CUR is equal to CUR left. What is CUR left? This becomes null. F does not have a left child. So next, CUR is not equal to null condition become false. We will come. So S dot pop. So if you pop, each element gets popped out, F gets popped out. So CUR will be made to point to F. So first F will be displayed and CUR. So S dot pop, F will be popped and it will be made to point to CUR. CUR now points to F, display it. Okay. And then CUR is equal to CUR right. What is CUR right? Null. Once again it becomes. So after becoming null, once again you go back. S dot empty. What is S dot empty? False. Okay, false is equal to false. We will enter into the loop. Current is not null. This condition becomes false. So we will come here. S dot pop. Which node gets popped out? D gets popped out. So series current now points to D. So then we will display D. And then CUR is equal to CUR right. D doesn't have right check. Once again it becomes. Okay. Then once again go back. S dot empty. So S dot empty is true. Okay. So sorry, S dot empty is true. What is the value it is going to return empty? So is it empty? No, it's not empty. It has C node. So S dot empty will return what? False. False equal to false. Yes. So current is not equal to null. So current is null. This condition becomes false. So we will come here. S dot pop. Which node gets popped out? C. So now your C current will point to C. Okay. So and then it will be displayed. Then current is equal to current right. Now you see current has right. So current now points to E. So after that, now once again you come back. S dot empty. So S dot empty is what is that? It returns true. So true is equal to false is false. Now current is not equal to null. Yes, this condition is true. So now CUR is not equal to null. So push CUR. So S dot push. So E node will be pushed. And then current is equal to current left. So E does it have left? No. So current is equal to null. So next, when you go back, current not equal to null condition becomes false. So we will come here. S dot pop. So if you pop, which element gets popped out? E. So E we are assigning to CUR. CUR once again points to E. So then display. So E will be displayed. And then current is equal to current right. What is current right? Null. So now once again you go back. S dot empty. What is S dot empty? So this now it is empty. So it returns true. True is equal to false. Its condition is false. CUR is not equal to null. So because E does not have a right check, so CUR right to CUR has become null. So now this condition becomes false and this condition becomes false. So we come out of the loop. When you come out of the loop, end of the function. When you come out of the function, so B, A, F, E, F, E, B, A, F, B, E, C, and then followed by E would be displayed. So even though this is small, so it has a lot of functionality. So what we are doing is, so first we are checking whether the stack is empty and current is not null. When both these conditions, when one of these conditions is true, we will enter the loop. When both the conditions are false, the function terminates. So if the current is not null, that is, if it is pointing to a node, what is that? We are pushing the node and then moving the pointer towards its left chain. So this we will continue until we reach a node with no more left chain. So when you reach a node with no left chain, then this loop will be terminated and we will come here. When you come here, what we will do? We will pop out the topmost node, display it, and make the temporary pointer point towards right chain. And then we go back and continue the same loop. So these are the steps. So this program has both recursive as well as non-recursive. So recursive, already I have given the definitions when we discussed binary tree or binary search tree. Already I have given the definition. So I have just shared the full program. So if there is any confusion, so you type the full program along with stack class, and then so recursive and non-recursive both definitions are provided in that the full program I have shared in your group today. You type that. So for your lab, you have both recursive as well as non-recursive. Only for in order it is there. So this is the in order. Any doubts? Okay. Now let us move on to height balanced binary trees. Okay. So before actually we discuss about height balanced binary trees, or otherwise AVL tree, I would like to once again, I don't know, several times I'm using this term, uh, height balanced, height balanced. What do you mean by height balanced basically? Can anybody tell? Height balanced binary tree. What do you mean by height balanced binary tree? So several times I'm using this term, height balanced, height balanced. What do you mean by height balanced? Yeah.
When both the children have same height.
When both the children have
Same height, sir.
Height is fixed.
fixed to what? Okay. See here. Suppose so here, what is n? How many elements are there? 1, 2, 3, 4, 5, 6, 7, 8. So we have taken n value as 8. N value is nothing but the number of elements that we are considering. Number of key values. Okay, let us construct a binary search tree. So first 2 will become the root. So 3 is greater than 2. So 3 will become the right child. 4, okay. 4 is greater than 2, 4 is greater than 3. So 4 will become the right child of 3. Next 5. 5 is greater than 2, greater than 3, greater than 4. 6. So 6 will become the right child. 7 will become the right child of 6. 8 will become the right child of 7. And 9 will become the right child of 8. Now, so with this given set of values, so it has resulted in a right skewed tree. So this tree is known as, because all the children of this tree are oriented in only one direction. So if all the children of a tree, binary tree, if they are oriented in the left direction, then it's called as a leftist or left skewed tree. And if they are oriented in the right direction, then it's called as a rightist or right skewed tree. So this is a right skewed tree. Now, for example, I want to search for 9. I want to search for 9. So how should we search, or what is the procedure for searching for a given element in a binary search tree? So first compare it with root. Okay, first comparison. 9 is greater than 2. Does not match. So because 9 is greater than 2, take the right direction. So second comparison. 9 with 3. 9 is greater than 3. So it does not match with 3 and it is greater than. So take the right direction. 9 compare with 4. So third comparison. So 9 does not match with 4, but it is greater than 4. So take the right direction. 9 with 5. Fourth comparison. 9 with 6. Fifth comparison. 9 with 7. Sixth comparison. 9 with 8. Seventh comparison. 9 when you are comparing with the last element, that is the 8th element. Now your search was successful. So the element you are searching for was found at the end of the binary tree. Now in this binary search tree, so totally there are n elements. There are 8 elements, and for searching for element 9, we took 9 comparisons. So this is nothing but it has become a linear search. So linear search. So here, can anybody tell what is the height or depth of this tree? Height or depth of this tree? What is the height or depth of this tree?
8.
Yes. Height or
8.
yes, depth of this tree is 8. So in the worst case, so suppose if with n elements, so if you create a binary tree with height n, in the worst case, you may require n number of comparisons to search for an element. So if I want to decrease the number of comparisons, so if I want to decrease the complexity of the search operation, then what is that I need to do? I need to decrease the height of the binary search tree. So if I can restrict the height of the binary search tree to something, then the number of say for example, if I restrict the height of the binary search tree to log n, so then in the worst case with log n number of comparisons, I would be able to tell whether an element is present in that binary search tree or not. So if you don't restrict, the worst case, so with n number of elements, if you construct a binary search tree, in the worst case, you may require n number of comparisons. That is, so insertion, deletion, and search operations in a binary search tree, in the worst case, may require big O of n time points. So, say for example, I want to insert 10, compare with 2, compare with 3, compare with 4, compare with 5, compare with 6, 7, 8, 9. So finally 10 gets inserted. So n is nothing but n is n 8 here. 8 is nothing but small n. So insertion time complexity is big O of n. Similarly, deletion also, if I have to delete 10, first I have to search and then I have to delete this 10. It also requires big O of n. Search also, if I am searching for 10, maximum of n 9 comparisons are required, which is equal to n, big O. So your insertion, deletion, and search operations in a binary search tree requires big O. So they work with big O of n time complexity. Now, see, now it has become almost a linear search. So why we have to construct a binary search tree and then use it for insertion, deletion, and search operations when its time complexity is big O of n? Straight away you can use a linear search. No? There is no purpose because it does not serve any purpose because the time complexity is big O of n, which is almost an equivalent to a linear search. So that is why what we do is we try to restrict the height of the binary search trees to log n. If you can restrict the height of the binary search tree to log n with fair number of comparisons. See, n if it is 100, log n approximately would be around 9. With only 9 comparisons, you'll be able to tell whether an element is present or not in a list of 100 elements. So if n is 10, approximately log n value would be 3. So with only 3 comparisons, you'll be able to tell whether an element is present in a given list of elements or not. So your binary search works with log n time complexity. So that is why So in order to create a binary search tree, which has big O of log n time complexity for insertion, deletion, and search operations. So they did a lot of research. And finally, in 1962, 3 persons from Denmark. So Adelson, Belsky, double I, and Lands. So these are the names of the 3 persons. So with their names, now this height balanced binary search tree is named as AVL tree. Adelson, Belsky, Landis trees. Okay. So AVL tree has, it is nothing but it is also a binary search tree. The first property of AVL tree is it is a binary search tree. So what is a binary search tree? So binary search tree is a binary tree. Basically, any node can have maximum of 2 children. So that first property it should satisfy. Now what is the second property it should satisfy? Node value should be greater than its left subtree and node value should be less than its right subtree. So this property it should satisfy. Okay. So it is a binary search tree. Apart from that, it should also satisfy one more property. What is that property? So mod of HL minus HR should be less than 0. Okay. So mod of, okay. So HL represents height of the left subtree and HR represents height of the right subtree. So HL minus HR should be less than or equal to 1. HL minus HR should be less than. So if a binary search tree, if it satisfies this property, then it's called as an AVL. I'll explain this about this HL and HR in a moment. Okay. See, now this HL and HR, this difference HL minus HR sometimes is also known as balance factor. So it's called as balance factor. So otherwise, you can define an AVL tree as a binary search tree in which all the nodes binary balance factors should be either -1 or 0 or 1. So that is, if you restrict the balance factors of all the nodes in a binary search tree to only 3 values, either -1, 0 or 1, then such type of a binary search tree is known as an AVL tree. So what is this all about? Let us try to understand. So I'll give some examples. Okay. So first, let us consider a binary search tree with only one node. With only one node. What is the value stored here? 20. Now, what is the height of its left subtree? It does not have left subtree, does not have right subtree. So what is its balance factor? Its balance factor is 0. Balance factor is height of left subtree minus height of. So it doesn't have left subtree, doesn't have height of left subtree is 0, height of right subtree is 0. So HL minus HR is 0. Okay. Now I consider one more case. 20 has a left child. So is it a binary tree? Yes. Is it a binary search tree? Yes. Now, can we call it as an AVL tree? Now, let us calculate the balance factors. Okay, what is the balance factor? Okay, so generally, we have to calculate the balance factors always from the leaf node level. So come to 10. So what is this balance factor? Leaf node balance factor is always 0. So it does not have left child. So HL is 0. HR is also 0. So HL minus HR is also 0 for this one. Now, how to calculate balance factor for this 20? Tell me. What is the height of the left subtree? Height of the left subtree is 1. Height of the right subtree is 0. So what is HL minus HR? 1 minus 0 is 1. So balance factor of this node is 1. Next step is, in order to decide whether this is an AVL tree or not, you have to check the status of the balance factors of all the nodes in that tree. What is the balance factor? 0. What is the balance factor? 1. So if the balance factors of all the nodes in a given tree are either -1 or 0 or 1, then such type of a binary search tree is known as an AVL tree. Now, I'll take another example, 20. Can anybody tell, is this an AVL tree or not? Is this an AVL tree? Yes.
Yes, sir.
Yes, it is AVL tree. What is the balance factor? 0. 0. What about this? 1. What about this?
1.
This is 2 minus 1. So right subtree is 1. So 2 minus 1 is 1. So 20 balance factor is 1, 30 balance factor is 0, 10 balance factor is 1, 5. So all the nodes balance factors are within the permissible range. Either they are 1 or 0. So now it is an AVL. Now let us add one more chain. Okay. Now you tell me, is this an AVL tree? Is this an AVL tree?
No, sir.
Yeah. So here 3, this is 0. 5, this is 1. 10, this is, what is the height of its left subtree? 2. What about this? 1, 2, 3 minus 1 is 2. So this particular node and this particular node balance factors are not within the permissible range. So here, why we are considering balance factors? Just try to analyze why. What is the importance of this balance factor? What it is telling us? So when the balance factors are not -1, 0, 1, what is that? See, suppose if the height of your balance binary search tree, if it is log n base 2, then all the nodes will have the balance factors of -1, 0, or 1. So when the height is not restricted to log n base 2, then one or more number of nodes balance factors goes out of scope. Out of scope means they will become 2, 3 lines. Now, for example, in this, if I'm searching for 3, so how many comparisons I require? First comparison, second comparison, third comparison, fourth comparison. So totally, how many elements are there? 5 elements are there, and we require 4 comparisons. Almost all it is reaching the O of n. It is not log n. So n minus 1 comparisons are required. N is 5, 4 comparisons means n minus 2. It's not log n. So that is, the number of comparisons are becoming more. So that's why. So when the balance factors of the nodes are -1, 0, and 1, it means that the height is restricted or height is within the reach, that is within log n base 2. So when it exceeds, when the height or depth of a binary tree exceeds log n base 2, then one or more nodes balance factors will go out of scope. That is, it means that it's not a height balance. Its height is not restricted to log n, and it is going beyond log n. So then one of the nodes balance factors will be not among -1, 0, and 1 values. It will go 2, 3, something like that. That means it's not height balanced. That is, so with log n base 2 number of comparisons, you will not be able to perform search operation, insert operation, or delete operation. So once again, what we need to do is, we need to bring this node once again to a balanced state. Balanced state means we have to restrict its height to the O of log n base 2. So for that, we will apply a technique or a scheme known as balancing. So this is most important. So this is an unbalanced tree. Why it is not why it's called as unbalanced tree? Because the height is not restricted to log n base 2. So whenever its height is not restricted to log n base 2, then we say that it is an unbalanced tree. So again, we need to bring it to balanced state. Balanced state means, so tree having a height that is less than log n base 2, height or depth. So for that, we have to apply a scheme known as balancing scheme. So we need to once again bring it back to a balanced state. So for that, we need to apply so balancing technique, or sometimes this is also known as rotations. We have to apply some rotations, and we have to bring that unbalanced tree to back to balanced binary tree state. So for that, we need to apply rotations. So next class, I will discuss about the 4 rotations that we use in AVL trees, and we will also discuss one example. There's one very popular example for AVL trees. So the same question was asked 2 times for your end exams. So I'll discuss that question in the next, that is on in Monday's class. So I'll first discuss. So once again, I'll try to review what is this AVL tree. So then while constructing a, so here already we have constructed a skewed tree. So skewed tree is not a balanced tree. It's because its height is not within log n base 2. So it's not a balanced tree. How to bring that skewed tree back to balanced state, we will discuss in the next class. If you have any doubts, you ask me.